Hey everyone, my name is Anthony Spradling. Thank you for joining me today. In this presentation, I'll be walking you through my MATLAB project for ME1311, the creation of a 2-day solar system. This project combines real-world astronomical data with core principles from physics and MATLAB programming. It is designed to simulate the orbital motion of 8 planets in our solar system in a simplified 2D space. Over the next few minutes, I'll explain the problem I set out to solve, my approach, the physics behind the model, the code structure, and finally some example outputs that showcase the result. So let's start by discussing the problem I was trying to solve. My goal was to create a two-dimensional model that simulates the solar system using real data from NASA's planetary fact sheet. The purpose of this model is to predict and visualize the movement of the planets in orbit around the Sun. A unique choice I made for the simulation was to treat each planet as an independent two-body system, meaning the only gravitational interaction considered is between the Sun and the individual planet. This simplifies the calculations while still yielding realistic orbital behavior. I also wanted to give answers to give the users the ability to adjust two key simulation parameters: the total duration of the simulation and the time step. This makes it possible to explore planetary motion over a single season, a few years, or even decades, depending on what the user wants to observe. Here we have the general flowchart of how the program works from left to right. First, we define the gravitational constant we will be using in the program later, or just in general the constant we will be using later. We define the gravitational constant, atomic unit, and iterative time difference. G, the gravitational constant, is 6.67 times 10 to the negative 11. The astronomical unit is 1.49 times 10 to the 11. And the time differential is 1 day, which we have to show in seconds for MATLAB. The next step is to set up the initial planet data, which we got from NASA's website. This includes the planet's masses and initial position and velocities. We then set up a simulation for each planet. This consisted of calculating the gravity from the Sun based on the position of the planet in 2D space, updating the velocity based on Newton's second law, and restarting the loop for each time step. We then plotted the data we got from the loop. Here we have the equations we had to derive for the for loop. On the left, we have the fundamental physics principles you have learned in your Physics 1 class, and on the right, we have the versions that MATLAB understands with vector components. The first equation we needed was to find the distance of each planet from the star. We would use the distance formula to find this and use the positions of the planets in the x and y axis. In MATLAB, we use the Euclidean norm function. What we do next is use the velocity update formula to find the final velocity of the planet in that time interval of 1 day. In the MATLAB version, we must use a vector. What's next is the solution for the acceleration equation, and we did this by using Newton's second law and the force of gravity equation. This left us with the equation we have here on the right, which is the same as the equation we use in physics. We then needed to create a position update formula, which iterates over the time step to find the final position. We know the acceleration is 0 when the object is moving at a constant rotational velocity, so we end up with the equation we have here on the right. Now we move on to the MATLAB code. In this part, we can see where we have designated the constants we spoke about earlier. What we also see is how we set a variable that gives us the total number of years we want to run the program as t, and the number of time steps in the simulation, which is dependent on the time differential and total time t. We also set the mass of the Sun in kilograms. In the following lines, we created an array of the planets in the solar system and their respective masses, initial positions, and initial velocities. In the next lines under pre-allocation, we set the position and velocity and initialize the 3D arrays of all the planets. In the first for loop here, we set up the planet's positions on the x-axis as their distance from the Sun and 0y component. Here we also find the velocity and the rotational direction for each planet based on the regional velocities we set earlier. In the next line, we iterate using the formulas we spoke about earlier from the distance, acceleration, velocity, and position formulas. This is a for loop inside another for loop that tells MATLAB to do it for each planet in the index we described earlier. In this part of the code, we set up the plot results with a figure. We set the title of the plot to be planet orbits, the X label to be X positions in atomic units, the Y label to be Y position in atomic units, and set different colors for each line. In the first for loop, we create a plot for each planet using a unique color. In the final part of the program, we place a yellow dot in the center as the sun and create a legend with all the planets' names. Now we will look at some of the possible plots that can be made with this program. In this first example, I ran the simulation for 5 years with a 1-day time step. You can see that the inner planets like Mercury and Venus complete mini orbitals, while the outer planets like Uranus and Neptune barely move. They take decades to complete one orbit. This visual output is consistent with Kepler's third law, which states that the orbital periods increase with distance from the Sun. Here's a longer simulation, 30 years with the same 1-day time step. Now we can see much fuller paths for the outer planets, including multiple revelations for Jupiter and Saturn. The elegance of planetary motion becomes really clear here. You can see how orbits naturally arise from the laws of gravity and motion. This final example zooms in to just 1/4 of a year, about 90 days. In this case, we're looking at a very short window, so only Earth shows a noticeable movement around 1/4 of its orbit. This kind of short-term simulation can be useful for studying seasonal changes or focusing on specific events. Let's now switch over to a brief live demo of the MATLAB code. Here we just have the MATLAB code. I'm going to press run to show you how it works. So just once we press run, we get this figure, and that's really it. We can also go in here and change the time step by increasing this number of seconds, which would increase the amount of time in the time step. We can increase the amount of time that the simulation runs for. So here we have 5 days. We can change this to 10 days, etc. And that's really it. So now we'll go back to the slideshow. That brings us to the end of the presentation. I hope this gave you a clear understanding of how we can use MATLAB not just for computations, but also for modeling complex systems like the solar system. Thank you so much for watching, and I hope you learned something new. Feel free to reach out if you have any questions, and have a great rest of your day. Thank you.